Good morning. My name is Sonia, and welcome to Mechanical Ventilation, Whole House, and Local Exhaust. This is webinar 10 in the Building Smart program. This program is being brought to you jointly by DTE and Consumers Energy. My name is Sonia. I will be your instructor for today. I tend to have some connectivity issues with my internet. So I'm going to turn off my video camera during the presentation. I'll turn it back on at the end of the session for Q&A. But again, my name is Sonia. I'm excited to be your instructor for today. I've been doing this for a number of years and hope we have a good time today. What I hope that you will walk away from this seminar with, hang on one second, I've got a couple of monitors open. I need to get to the right screen. Okay, there we go. Okay. So what I'm hoping that you'll walk away from today with is a better understanding of the basic ventilation requirements and the ability to discuss benefits of whole house ventilation with homeowners who may be your clients. And then also to be able just to identify practical ventilation strategies. Here's the rundown for today's webinar. We'll talk a little bit about indoor air quality and ventilation, just kind of go over the basics. We'll talk about types of ventilation systems. We'll talk about ventilation rates, both for whole house and for local exhaust systems. We'll talk a little bit about combustion air, and then we'll wrap up with terminations. Before we get real started, I'll just kind of introduce myself a little bit, and then I'll ask you to introduce yourselves as well. So there's a little poll question that John will pull up for me. Thank you so much, John. And I will just tell you a little bit about myself. I've been in the industry for over 25 years. Started off selling commercial equipment, and then kind of moved into building performance improvement from there. John, I can't see the results. Actually, I need to switch to the other screen so that I can see the results when they pop up. All right. Looks like we've got mostly builders and contractors in the audience today. We've got a couple of code officials, a couple of engineers, but those builders and contractors. So welcome. I hope that today proves to be really educational for you guys, and that we have a better understanding again of whole house ventilation or ventilation requirements for whole house and local exhaust. I'm trying to close some extra windows that I've got open here. I apologize. Give me just a moment. Got a bunch of stuff open on my computer and it's not. I thought all this was closed. Okay, here we go. All right. So now moving on. So when we start with the house, right, when we think about homes, what do these buildings provide us, right? This is obviously where we do a lot of our living, right, and our playing. Increasingly, we are working from home, right? Our hours spent in the home have nearly doubled from post-COVID to pre-COVID. Just that event, right? That one event has kind of changed life for us here in America, and so we tend to spend a lot more time in the home, again because many of us are working from home now. But homes are also places where we sleep and we eat, we bathe, right? These provide our protection from the environment, right? From inclement weather. This is a place to gather with family, a place to store things, right? A space to do the things that we do as we're living. And so because we're doing that, we want these spaces to be clean and conducive to those activities. One of the ways that they are conducive is by providing good, what we call acceptable indoor air quality. Now, on the commercial side of things, we define acceptable indoor air quality specifically as air in which there are no known contaminants at harmful concentrations, um, and with which the substantial majority of occupants, defined as 80% or more, would not express dissatisfaction. For the residential market, we kind of pull that back a little bit. We don't put that 80% in there. We just say that it's air with which the majority of the occupants would express no dissatisfaction. And we specifically call out certain things that may be important to those occupants. So we're specifically looking at odor. We're looking at sensory irritation, things that might cause respiratory issues, right? But again, we've got this air inside this building that's there with intent, right? It's there for a purpose. It's to support the activities of daily living, and we don't want this air to be making us sick, right? So here are some of the factors or some of the things that present challenges to acceptable indoor air quality. Um, and you can see there are a number of them, right? So bacteria and viruses, we always knew these were a problem, but certainly COVID made that more clear to us that we don't want these things in our homes, right? Something that we don't always think about are cooking fumes, right? Cooking fumes release a variety of harmful pollutants into the air. They have smoke, the fine particulate matter. These things can get deep into the lungs. They can cause inflammation, which is, can cause all sorts of health issues. Um, and we think about this often with our other fuel burning appliances like our furnaces and our boilers and things like that. But we don't always think about with stoves that may be burning gas as well, that they can produce carbon monoxide, they can produce nitrogen dioxide, right? They can also produce VOCs, right, from fats and the other things that we're cooking at high temperatures. And these chemicals can present health concerns. Sometimes it's just something as simple as headaches or dizziness with overexposure. But for example, some of the VOCs that are released from cooking meats at high temperatures, these can produce some chemicals that are known carcinogens, right? Other pollutants, if you will, in the home could be paint. We're always, upgrading our homes and changing things around and redecorating. And paint also has VOCs in it, right? Some of these things, again, things like formaldehyde, benzene, toluene, these can be, some of these are known carcinogens. It also produces things that we know have neurological impacts on us. We also have cleaners in the home, right, with a number of chemicals that are in those. One of the things that we also potential factor that we have to mitigate for our homes is the presence of radon, right? This is a naturally occurring gas, right? And little known fact, it is the second leading cause of lung cancer in the US after smoking, right? We don't often hear that, but radon is that. Again, that second leading cause of cancer. Again, this is a naturally occurring gas. It can seep into the house from the ground, through the basement, through cracks and things like that. And it is specifically addressed. We're not going to talk a lot about radon, but I want to just mention to you and make sure that you're aware that it is specifically addressed in Appendix F of the Michigan Residential Code. And I know very often as we go through the code book, we may look at the various chapters when we're looking at things and we think, oh, that most of the appendices, we think that's just extra information that we don't really have to pay attention to. But there are some mandatory appendices, and Appendix F as in Frank, is one of them. And so we want to make sure that that we're aware of that for radon. So one of the other things that we don't think about that could potentially be a contaminant in the house and in the air is the moisture in the air, right? Uncontrolled moisture can it can damage wood, right? You may have an older home. You may see in older homes in Michigan, you know, the wood expanding and contracting as we change seasons, right? That's a sign of uncontrolled humidity levels in the home, right? And we've known since the mid 80s, right, that humidity, the relative humidity level inside buildings impacts human health, and it also impacts some of the other things that we don't want in our indoor air, such as bacteria, viruses, mites, and the like. So now this chart that you're looking at here on the right-hand side, this is probably pretty familiar to you. It's often cited. It's an ASHRAE chart that talks about the optimum zone for relative humidity. And we know that for humans, an optimal zone is between 40 and 60% relative humidity. Now, it just so happens that that optimal zone for humans is the inoptimal zone for the bacteria, viruses, and fungi and other things that we don't want to have in our air, right? So humans thrive between 40 and 60%. These other things that we don't want, right? They don't like that 40 to 60% range. They do better either above that or below that, right? And so keeping our homes in particular, where we spend, again, much of our time between that 40 and 60%, becomes really important. Now, here in Michigan, we're challenged with, you know, dry winters. And so we often see relative humidities between 20 and 30%, right? And we say, okay, well, if we can get it to 30, you know, that's really good. And that may be the best that you can do with the HVAC system that you currently have in place. But know that the goal should really be to be able to achieve higher relative humidity levels, right? To get it up between that 40 and 60%. And that may think that we need to do things differently with the house envelope, which, you know, we've talked about in previous webinars, and my co-instructor, Chris McTaggart, may talk a little bit about that later on in the webinar series when he talks about above code homes, right? Doing things to help control humidity a little bit better. One of the best ways that we know to manage indoor air quality, right, is providing air with fewer pollutants in it, right? And the best way to do that is to regularly or continually, either or, regularly or continually, dilute the air that's in the home, right? And so that's similar to if you this image here where we've got a cup of red fluid, right? So if it's water, and the red dye is a contaminant here, right? So the water should be blue, and it's red to show the contaminants here. And if we were to add clean water, right, to that cup, we're diluting the pollutants that are there, right? But they're still there. They're just diluted now. So to help get rid of them and dilute that air even further, we also bleed off a little bit of that fluid, bleed off a little bit of that air. And then you can see the difference here. So instead of having the dark red cup of water or fluid, you've got a lighter red, you've got a more pink cup of fluid. That represents diluted air, right? So you still have some contaminants there, but they're significantly diluted. And the more clean water you add, the more clean air you add to your system, right? The more diluted, the cleaner the overall air is. And so this process of diluting that air, that's what we call ventilation, right? So we're either adding air to or removing air from or doing both of those, right, to address the pollutants that are in the air, right? And this ventilation helps not only address physical pollutants, right, but also thermal pollutants. So temperature is controlled as with ventilation, as well as moisture. So humidity can be controlled with ventilation, right? Because we can either humidify or dehumidify, add moisture to, or remove air from that supply air that we're adding to the space. So ventilation comes in two primary forms. We've got natural ventilation, right, which relies on wind and stack effect, or the chimney effect, to cool a home without using the HVAC equipment. Right, so wind can naturally ventilate the home. It enters through open windows, through open doors, depending on the wind's orientation, obviously. And when that wind blows across the house or against the house, wind comes in one side and goes out the other. The stack effect. Similarly, you've got cool air that's entering the home, typically through lower levels. It absorbs a bit of heat, then rises, and then exits the home through upper levels, right? And this exiting the home through upper levels kind of creates a slight vacuum that allows more air then to come in, right? The second type of ventilation that we have is mechanical ventilation. This is a more controlled form of ventilation. It's using fans and mechanical and electrically powered equipment. And so because you've got more control, you've got a more consistent, more predictable, more reliable form of ventilation. Additionally, mechanical ventilation uses filters. Natural ventilation tends to not use filters, right? And so our current Michigan Energy Code requires mechanical ventilation. Natural ventilation can be used as a supplement or in addition to mechanical ventilation. But the primary ventilation has to be, there has to be some mechanical ventilation to the system. Ventilation, whether it's mechanical or natural, it's measured in units of air changes per hour, or how often the entire volume of air in the space gets replaced. And that space that we're talking about, that space could be a single room, or that space could be the entire house. The air changes per hour is calculated by multiplying the volume flow rate, cubic feet per minute, times just a conversion factor, 60 minutes per hour, and dividing that by the room volume, right? And that room volume is equal to one air change, right? Because if we're looking at air changes, we're talking about that entire room volume. Now, if you don't happen to know the room volume, you can the standard room you know the room dimensions, the room length and the width. Typical room height, particularly for older homes in Michigan, is about 8 feet. 9 feet is becoming a little bit more common, but most homes still are around that 8 feet mark. You may have some larger homes that have higher ceilings, cathedral ceilings. Sometimes in those particular cases, we have to certainly take some measurements. But if you're just doing kind of a swag at something, you can 8 or 9 feet for ceiling height is a good number. It's important to note here that this air change per hour value, right? This is the entire room volume or the entire house volume. So it doesn't mean that that entire volume, however, is outdoor air, right? A significant portion of that air is going to be recycled air or recirculated air, right? Air that's been collected by the air distribution system and then taken back to the central equipment, the furnace, the air handler, what have you, and then reconditioned, cleaned, filtered, heated, and possibly humidified, or cooled and dehumidified, and then sent back to the various rooms of the house to do more work, picking up heat. Required ventilation rates are based on the number of occupants in the home and the various room functions in the home. So we kind of divided up into just three broad categories: the kitchen, the bathroom and toilet rooms, and then the other general living areas. The ventilation rate is defined either in terms of volume flow rate, so CFM, cubic feet per minute, or in terms of air changes per hour. But note here that it applies specifically to the outdoor airflow rate per person, right? So even though we're looking at air changes per hour here, we're looking at specifically the amount of outdoor air that's being brought in, and in terms of air changes, not the entire volume of air for that space, for that room, or for that home, right? And so it's either in terms of depending on the space, that outdoor air that's either brought in, or indoor air that's exhausted and then replaced with outdoor air. So, for example, if we were to have let's say we have a living room that is 13 by 20 feet with an 8-foot ceiling, right? So our room volume is 2,080 cubic feet. If we were looking at to see, which value we would use here for our outdoor air flow rate, right? Because it's the higher of either 0.35 air changes per hour or 15 CFM per person. So if we looked here at the air change rate, this 0.35 air changes per hour, if we multiplied that by the cubic feet of the room, 2,080, and divided that by the 60 minutes per hour, we would end up with 12 CFM per person, right? Which would be less than the 15. So here we would use 15 CFM per person as that outdoor air flow rate. We want to make sure that we got that in the breathing zone for those living areas. The types of mechanical ventilation. So we've got two types of ventilation, and then we've got two types of mechanical ventilation. So mechanical ventilation can either be for the entire house, or it can be for specific rooms. Now, currently, our Michigan residential code and our energy code allow us to use either whole house or local exhaust. Later versions of the residential code on which the Michigan residential code is based are specifically calling out whole house ventilation under certain circumstances. We'll talk a little bit about that in a couple of minutes. But these are the two types of mechanical ventilation that you can have, right? So the whole house ventilation is going to take air out of the entire house and make sure that those air changes per hour are met for that entire house as a whole. Local exhaust is just going to look at specific rooms, your kitchen, your bathroom in particular. The ventilation rate, right, is based on the size of the house, again, and the number of people that are expected to be in the house. And we use as a representative of those numbers of people the number of bedrooms that are in the home, right? So again, here in Michigan, whole house ventilation is not required. It can be local, but it just has to be mechanical. Now, because many newer homes have tighter construction, again, the later versions of the energy code are going to require that that homes with infiltration rates less than 5 air changes per hour at 50 pascals use whole house ventilation. Right now, however, that's again not something that we're requiring here in Michigan just yet. Um, and again, my co-instructor Chris may talk a little bit more about that when he talks about beyond code in some of the later sessions. So again, these are the rates for continuous ventilation for mechanical systems. The ventilation rate doesn't have to be continuous. It can also be intermittent, meaning it can start and stop. Now, when you use an intermittent rate of ventilation, it has to be higher than the continuous rate. It has to be higher because it has to compensate for reduced fan runtime. For every 4-hour period, the intermittent system has to provide a ventilation that's equivalent to what would be provided under continuous operation. So, for example, if the system were to only run half of the time, then the intermittent ventilation rate would have to be twice the continuous rate. And the system has to operate at least 60 minutes in every 4-hour period. This can be one of every 4 hours, or it could be 15 minutes every hour. The choice is up to the designer. With this table that comes from the Michigan Residential Code, you can interpolate in this table, but you cannot extrapolate. So you can't go, obviously, you wouldn't go higher than 100%, and you can't go less than 25% of the runtime, right? So that means you have to be operating between these two limits. Okay, so let's take a look at a quick example here. If we've got a house that's 2,300 square feet, 4 bedrooms, what is the ventilation rate if this fan runs continuously? So in this system, if the fan were to run continuously, we've got 4 bedrooms, so it's going to be this column here to the far right, and the house is 2,300 square feet, which falls into this range right here between 1,500 and 3,000, and the intersection of these two is at 75 CFM. So that would be the continuous airflow rate for ventilation for that house. But now if the fan were to only run 30% of the time, we'd go to a different table. We'd come over here, and again, we can interpolate in this table. So we would look, we know that it's going to be somewhere, we're going to have a multiplication factor between 3 and 4 here. So we would interpolate to find that our factor, our multiplying factor is 3.375. And then we would multiply that factor by our 75 CFM, which would be our continuous rate. And we would see then that the ventilation rate we would have to provide would be 254 CFM. And that would be for a fan that ran, again, 30% of the time. So that's either going to be 20 minutes out of every hour, right? Or about 72 minutes for every 4-hour period. So let's take a quick poll question here. And I'm going to ask you, what would be the ventilation rate for a 3-bedroom, 1,500 square foot house if the fan ran 75% of the time? And you're going to need a couple of tables in order to answer that question. So I'm going to give you those tables. They're right here. And we'll give you just a minute to answer that question. Let me switch screens so that I can see the responses. Okay, do we have responses, John?
Yeah, we do. We have 5 out of 10 participants have answered the question.
Okay, I'll give you guys another minute and then we'll just go ahead and we'll post those responses. Don't be afraid. Nobody knows what your answer is, and we're all here to learn, right? Okay. John, why don't you go ahead and, oh, you've posted them. Perfect. Thank you so much. All right. So let's see here. 60% of you have said 45, and 40% of you have said 58.5. And to get to the correct answer is 58.5. And how we achieve that is we know that we've got 3 bedrooms and it's a 2,300 square foot home. So we know that our, wait a minute, what? Oh, I'm sorry, 1,500 square foot home. The 2,300 square foot home was the first home. It's 1,500 square foot home. So our airflow rate for continuous airflow is 45. And we know that we're going to have to multiply it by a factor over here. And we said that the fan is going to be running 75% of the time. And so we're going to multiply that 45 by the factor for 75%, which is 1.3. And that's how we end up with our 58.5. Okay, let me switch back to my other screen now. Okay, so we've talked about the types of ventilation. Now let's look at the various types of mechanical ventilation. So mechanical ventilation falls into 4 primary types. The first and the least costly type of mechanical ventilation is what we call exhaust-only ventilation. You see this often in, you may see this in some older homes. I live in Detroit in an older home in the city, and this home has a kitchen exhaust fan. My parents' home also had a kitchen exhaust fan, so a lot of our homes had kitchen exhaust fans. You also see exhaust only ventilation in small commercial buildings. They may have exhaust only. They will tend to have those exhaust fans in the bathroom, right? And that's how they are bringing in fresh air. And again, you're bringing in that fresh air because as you're exhausting air out of the home, that creates a slight negative pressure, slight vacuum that allows more air to come into the home. Now, the downside with exhaust only ventilation is that you don't have a you don't have a means of purposefully supplying that outside air. So that outside air that's being brought into the home through that slight vacuum is coming in through cracks and crevices around the home, through the space around windows and doors. And the other thing about that outdoor air that you're bringing in, it's not tempered, right? It's not filtered, right? And it's coming through again these cracks and unsealed penetrations and things. So that the quality of that air may not necessarily be of the caliber that you want in the home. The next form of mechanical ventilation is supply only ventilation. Now, here you are supplying fresh air to the home. This is the opposite of the exhaust only. So you're bringing in fresh air, you're creating a slight positive pressure. And so you're pushing out, you're exhausting air, that exhaust air is being pushed out through cracks and crevices in the building envelope. So here you may or may not be conditioning that air that you're bringing in. Oftentimes, you will certainly be able to filter that air, so you can do that. Sometimes the supply fan may be connected to the central fan. It can be connected to the central air handler or furnace in the home if it's a forced air system. And so then you're able to bring that air in and then condition it that way, right? Or you may have a dedicated supply air system where you've got a filter and a tempering piece of equipment in that system directly. These systems are a little bit more involved, and so they cost a little bit more than the exhaust only systems. The balanced ventilation approach, this has both a supply and exhaust fan. And here you are bringing air into the home and then you're exhausting almost as much as you're bringing in, maybe a little bit less than what you're bringing in, right? So the supply and exhaust rates are roughly equal, right? This also can be a standalone system, or it can be integrated with your with the central system. The fourth type of mechanical ventilation is what we call balanced ventilation with recovery. This uses a special heat exchanger that allows the air that you're bringing in and the air that you're exhausting to transfer energy between each other. Now they are physically isolated so that you don't get any contaminants that you have in the air that you're exhausting. You don't mix those contaminants with your supply air, but you are able to exchange thermal energy between the two. And this device that does this exchange is what we call a recovery ventilator. That recovery can either be sensible heat only, so it can just be temperature change, or it can include moisture, right? So it could be sensible and latent heat. When it includes both sensible and latent heat, we call it energy recovery. This system is more involved, requires more controls. We don't see this in older homes, but we do see this unless they've been renovated. But we do see this in newer homes, particularly larger homes. This is a system that we often see in commercial applications as well. Right. So this is kind of what the overall mechanical ventilation system might look like for those with those four types. So here you've got, your house, I've got a kitchen shown here, various locations for the filters. So that could be the filter can be located in a number of places depending on what other equipment is in the system. Traditionally, filters have been provided for the benefit of the equipment, to protect the equipment. But today we use those filters to protect the occupants as well. And so in addition to filters, we may use air cleaners in addition to them. But they can be located a number of places. The most common place is on the return side, just before you enter the furnace. So the air, you can see, can take a number of different paths through this system. Typically, coming in from the return air in older homes, this would just be recirculated and it would go straight back to the furnace and get recycled through the home. In newer systems, again, with mechanical ventilation, a portion of that return air can get exhausted, and then some of it can come back either to the furnace directly or it can go through a recovery ventilator. And then also with the kitchen, depending on how big the ventilation system is for the kitchen, you're definitely going to have some local exhaust, but depending on how big that system is, you may also have some makeup air that's coming directly into the kitchen, in which case you would have an air cleaner or filter there as well. So now let's take a look at what the components of this system are. So we've got some, one of the things that you're going to have in your system is some backdraft dampers, right? We want to make sure that we aren't re-entraining used air. We want to make sure that we don't have untreated infiltration air come back into the house when the system's not running, right? So this backdraft damper will open when the fan is running, and when the fan's not running, it's going to close. It can either close by gravity, it could be a spring. In commercial applications, we would see motor-driven dampers, but here gravity or spring-loaded damper are just fine. When we think about the fans for those systems, there are some criteria for the efficacy or the efficiency of those fans. We want to make sure that they're not wasting energy. And the efficacy of those fans are based on their location within the house. A whole house fan would fall into this inline category here. So we would want to make sure that its efficacy was at least 2.8 CFM per watt, right? And you can see here, there are various locations where those fans might be for those for that local exhaust, either in the kitchen, the bathroom, or it could be the whole house. That ventilation system might be a once-through system, or it could be a recirculated system. Recirculated would be similar to, we've got these controls in our car that we may be more familiar with. These two images here, one is showing you where you're bringing in fresh air into the car, and then the other one is you're just circulating the air that's already in the car. All right, and so that's similar to what we're doing in the home. In commercial applications, it would be based on the classification of the air. For residential applications, we actually just define it, but we have basically 4 classes of air, some of which can be recirculated throughout the house and some can't, right? So class 1 air, it's got low contaminants, low issues there. And then class 4 air is highly objectionable air that cannot be recirculated. For the residential applications, we don't complicate things with defining the classification of the air and whether or not it can be recirculated. For single family homes, the code just simply says exhaust from bathrooms and toilet rooms shall not be recirculated, right? They can't be recirculated in one house, and they can't be taken out of that house and then used in another dwelling unit either, right? They have to be just exhausted directly outdoors. We talked about the heat recovery. So some pros and cons of those heat recovery units. They help to reduce HVAC costs, right? Because if you can exchange thermal energy between those two airstreams, if you can extract residual heat in the air that you're going to be exhausting out of the home, and you can use that heat to preheat air that you need to heat up into the home. So then you don't have to run, so that the furnace doesn't have to put in as much heat, or the vice versa if you're doing cooling, right? A pro for this is also that it requires, this were a presentation that was presented to homeowners, this might not necessarily be, they might not consider this a pro, right? Because that's going to increase costs. But for this audience, with technical folks, with code officials and contractors and such, this is a pro, right? Because this means that this requires you and your expertise. This gives you an opportunity to talk to the homeowner. This gets you in front of them to share your knowledge and what you know about the system. They do, however, tend to cost a little bit more, and they require freeze protection, so they require more controls, more enhanced controls, and they require a bit more maintenance. But these are still valuable things that we want to, if we can, we want to include these in our newer homes because they do help save energy. Whenever we have these mechanical ventilation systems, we've got to have controls for them, right? So we want to have controls that are going to help us with those duty cycles, particularly if we're using intermittent ventilation. So there we're going to have some controls that are going to be based on either, they could be based on time of day, they could be based on how long the equipment has run. But we also want to be looking at the indoor and outdoor air conditions, right? If we're bringing in outdoor air, with intent, right? We want to know what those outdoor air conditions are. We want to know what the conditions of that outdoor air is before we bring that into our system, so that the HVAC system knows what it has to do to keep the home comfortable, right? The code requires that those systems have a manual override capability, meaning the homeowner needs to be able to go up to the controller and tell it to stop, or tell it to start, or tell it to change levels. Right? We need to be able to have an override there. Some of the best practices with home house ventilation. Obviously, you want to select the most practical system for the particular application. So it's not always that that you need to go to the full blown system with the energy recovery. It may be that this is a smaller home. And it very well may be that supply air ventilation is sufficient, or even exhaust air, right? There are homes where this still may be sufficient. But we do want to look at, certainly where we can apply the balanced approach, or the balanced approach with energy recovery or heat recovery, when it's practical to do so. We want to lay out the design and the ductwork to make sure that we're going to get the airflow rates that we need, right? We know that we have to have certain ventilation rates. We want to make sure that we're going to be able to achieve those. We also want to make sure that we're inspecting and commissioning these systems as we're installing them, because they're more complicated. This is not your simple, older traditional home, again, with just your exhaust ventilation system, or even some homes with no ventilation systems, right? So you want to make sure that this technology that you're bringing into the home is going to work properly and do what you're intending it to do. So you want to make sure that these systems get commissioned. And then you want to make sure that you educate the homeowner on how to maintain and operate these systems. Now, the system, again, doesn't have to, here in Michigan, it doesn't have to be whole house ventilation. We can use local ventilation. And again, that applies to the kitchen and to the bathrooms. And when we do that local ventilation, it also can be either continuous or intermittent. When we're doing local ventilation, again, we're looking at specific rooms. We're interested in the kitchen in particular, right? So we're going to have a range hood. This is going to go above the stove. And this will help to prevent odors from becoming trapped in the home. You're going to have those backdraft dampers that we talked about there. You want to make sure that you're not re-entraining this air into the home. You're also going to make sure that you've got some smooth ductwork for that. It's either going to be galvanized steel or copper. If you happen to have, and these materials apply specifically to overhead hoods. If you happen to have a hood that's in the stove and it uses a downdraft system, so it's pulling that air down, right, and then exhausting it out of the home, the code does allow for Schedule 40 PVC to be used. When the kitchen system is exhausting more than 400 CFM of air, we definitely want to have makeup air, right? You've exhausted a significant amount of air. We've got to make that up, right? So we're going to have a makeup air unit to do that. This unit will then bring in the amount of air that's necessary to balance what we've exhausted from the home. Here in Michigan, we would want to have a mechanical system, right? And it would also, again, have a backdraft damper, and it could be supplied either directly or indirectly to the kitchen. For bathroom exhaust, we want to make sure that this is an independent system, independently ducted. independent from the kitchen system and from the other ventilation system. We want to make sure that for the bathroom, we either have to have some openings in the bathroom, so you have to have an operable window or mechanical exhaust. If you whatever system you have needs to be able to convey both moisture and air, right? Because the bathroom air is going to be moist, and you want to make sure that it's far enough away from any intakes so that you don't get any re-entrainment. Again, you're going to have some backdraft dampers, and this is one of those air streams that for which recirculation is not allowed. Some of the things that we don't often think about when we think about ventilation, we don't think about some of the other appliances that are exhausting air from the home that we need to give consideration to as we're looking at what the ventilation rate needs to be. So we've got, homes have dryers, right? Now, this would not apply to condensing dryers or to heat pump dryers because those are ductless. But for ducted dryers, those natural gas dryers that are that have ducted exhaust, right? We want to make sure that exhaust goes directly to the outdoors, that it doesn't go to an attic or a crawl space. It doesn't go to a ridge vent or anything like that. We want to also make sure that this duct is supported. We've talked about making sure that ductwork is supported in previous sessions. And something to note here in Michigan is that, which is different from what the International Residential Code allows. Here in Michigan, we do not allow screws in this dryer exhaust ductwork, right? Those screws could potentially entrap lint and create a fire hazard. And so we don't allow screws here. We also don't allow screens. And we want to make sure that ductwork is a smooth metal, right? So this here, right, we would prefer that this be a smooth metal. We also need to give some consideration to exhaust from our furnaces and boilers and water heaters. These are other areas where we are exhausting air from the home, and that will also impact the ventilation, the balance in the home. So when we talk about, having that balanced approach, right, we want to make sure that we're accounting for the exhaust that we have from these other appliances. Some of the things that we want to make sure that we don't do as we're exhausting air, right? We want to make sure that those dryer vents are as straight as possible, that they don't have too many 90-degree bends, and that they vent directly to the outdoors. So we've got some things that are wrong here in these pictures. And so here we've got a closed dryer that's venting here. We've got an elbow here, and then it doesn't actually terminate outside. So we definitely don't want to do something like that. We definitely don't want to terminate into a crawl space or anything where we can potentially create problems with additional moisture, right? Creating damp environments that can harbor mold and rotting insulation and things like that. We definitely don't want to have too long of a duct run with a bunch of elbows here, where we end up with a dryer duct that's full of lint. Again, this could create a fire hazard. And we don't want to screen over that either, because again, that could trap lint. We've got a quick poll question here. I'm just going to give you just about 30 seconds to answer this question. And so the question is, what's the exhaust airflow rate, or at what exhaust airflow rate is a kitchen makeup air unit required? And I guess I need to switch screens so that I can see the question. Or see your responses, rather. Okay, John, do we have any responses?
Yeah, we have about half of the people have answered.
Okay. We'll give you another couple of seconds here. Okay, so most of you got this one right, and it is 400 CFM. So if you've got a local exhaust system for your kitchen that's exhausting more than 400 CFM of air, then a kitchen makeup air system is required. Now, you can certainly include a kitchen makeup air system if you want for lower exhaust values. So if you had a system that was exhausting 200 CFM and you wanted to provide some makeup air, um, because you want to make sure that that air is conditioned, you can certainly do that, and you can bring that directly into the kitchen, or you can do that through your central supply system. But the actual value is 400 CFM. At that point, the kitchen makeup air system is required. All right, so looking at the other equipment that you've got in the system, uh, your all of this fuel burning equipment requires combustion air. And so for your mechanical room, if you will, and typically in the house it's just the basement, or we might call it a furnace room. But for your mechanical room, the size of that room has to be able to provide that combustion air that you need for good ventilation. And so you can either size that room based on the total MBH input of all of the fuel consuming equipment, or you can look at applying different values for equipment that uses a fan and equipment that does not use a fan. Right? But we want to make sure that our mechanical rooms are sized properly, so that we get the proper amount of combustion air for our appliances. We look at those intakes, when we look at those rooms, we could also, in addition, other than taking the air directly from the space, we could bring in air from adjacent spaces. And so we can draw combustion air from an adjacent space if that space has a volume that is at least 50 square feet for every 1,000 MBH, or for every MBH of capacity that we have for all of the equipment. And we've got to have at least two openings, one within 12 inches of the top of the room and one within 12 inches of the bottom of the room, right? And then the size of those openings, right? Because this is just free air flowing between two rooms. It's either going to be, you know, the greater of either 100 square inches or 1 inch per every MBH for spaces that are communicating on the same floor, right? Or 2 inches. So you're going to have a bigger opening if you've got equipment on different floors. You could also bring in combustion air directly from the outdoors. If you did that with two openings, then you would need to have either an opening of 1 square inch for every 4 MBH or 4,000 BTUs per hour, for again the total capacity of all the equipment. And this is specifically for either vertical ducts or a direct opening. If you had horizontal ducts, those are going to have a little bit higher resistance, so we're going to have a bigger opening. So we're going to have 1 inch per every 2 MBH, and you still have to have those two openings within 12 inches of the top and bottom of the floor. I'm sorry, top and bottom of the room. If you only had one opening, right, then you're going to have 1 inch for every 3 MBH of equipment capacity. And you're going to have that opening within 12 inches of the top of the room, and you're going to want to be sure. Maintaining clearances is always important, but it's especially important if you've only got one opening. You want to make sure that you've got not just clearances for service and maintenance, but you've also got clearance for sufficient airflow. You could also bring in that combustion air. You could do that with a fan. So you could, again, we just talked about having just openings and just having natural flow of air. You could do that mechanically as well. So you could have a fan, and then the requirement is then that you have 0.35 CFM for every MBH of total capacity in that space. Whenever you've got a fan, you want to make sure that the fan is interlocked with the equipment in the space, so that whenever the equipment is running, this fan is open. And you want to make sure that when the equipment's not running, that the fan is closed and that the backdraft dampers there, the dampers are closed, so that you're not bringing in unwanted outside air. And note that this ventilation rate is independent of the other ventilation rate that you've got going on for the rest of the house. So this is in addition to that. You want to make sure that when you're looking at your ducts and your terminations, that you stay specific distances. In this particular case, 10 feet from hazardous or noxious contaminants. So if you've got vents from other appliances, you want to make sure that you don't have any intakes that are near those things, right? You don't want to be exhausting air onto walkways, onto sidewalks, into certain spaces in the backyard where people are going to be walking. So you want to make sure that you stay clear of those. And for you also want to make sure that your ducts are that they meet the limitations for length, right? Longer ducts tend to have more resistance, and they can reduce system effectivity. They can reduce efficiency. So we want to make sure that we adhere to the length limitations for ducts and terminations. All right. We also want to make sure, and I know that I'm over 12 o'clock a little bit. I'm going to take about 3 more minutes. We're just about done. If you could bear with me, that'd be great. If you have to sign off, I understand. But I'm just going to wrap this up real quickly here. We want to make sure that we seal those ducts in accordance with standards, right? Our industry standards, our manual D for our duct design. We want to make sure that that they're properly sealed. We talked about this a couple of weeks ago in a webinar as well. So we want to make sure that we adhere to those standards to make sure that those things are properly either gasketed, used mastic, welded if necessary, or proper sealants that are UL listed. We want to make sure that we also take into consideration in the design of our system the effort to prevent backdrafting, right? So this is backdrafting is the reverse flow of gas in the flue. So we've got this slight negative pressure that happens that can happen with fuel-fired appliances where we're exhausting out of them. Out of the building, and so sometimes those gases can be re-entrained into the vent and come back into the living space, and we want to prevent that from happening. Most furnaces these days have sealed combustion or reduced draft fans, and so we don't have this, but we may sometimes see this with older water heaters that have atmospheric draft, or we may see this with older boiler systems. So we want to make sure that we've taken steps to prevent that. And we've got another poll question, which we will skip over, and I'll just tell you the question and the answer. The question there was, where is the Michigan residential code addressing radon? And that was something that we talked about at the top of the hour, and that is addressed in Appendix F. That's a crucial one of the required appendices that is part of the code. And with that, I'm going to I'll entertain any questions. And while we're doing that, I'm going to move on to just the next slide to let you know about the next session, which is going to be HVAC controls and right sizing. That will be next Tuesday, the 29th, at 11 a.m. And I'm going to turn on my camera now and see if there are any questions. And if there are, I will entertain them. If not, we will let you go ahead and get out of here. Okay, well, I'm not going to keep you longer than I already have, because we've gone over. So I'm going to say thank you so much for attending this session, and we look forward to seeing you next week.